very pleased to welcome our next speaker, Chris Lloyd. I think Chris has spoken at every variable star section meeting I've been to. We always like to invite Chris along with the perspective he brings. Chris is a former researcher at the Rutherford Appleton Laboratory and is a great supporter of the variable star section. Earlier I mentioned the work he's done to make the variable star section circulars available through the NASA AVS system, and we're very grateful to him for that. So Chris likes nothing better than crunching numbers. His main activity, but he's also, I happen to know, he's also a visual observer. And if you go to the photometry database, you'll see quite a few visual observations, notably a long run of beta drills.
Yes.
One of his favourite stars. Chris was also my partner in crime, and I think we can probably confess this at the last Winchester meeting.
I think it's already out there.
We skipped one of the talks to actually go out and observe it, and we made a scientific observation that night, didn't we?
We did.
We determined the visual magnitude of beta drills,
which I later corrected for extinction.
Fantastic. So Chris is going to tell us about what can eclipse timings tell us. Chris, over to you.
Thank you. Thank you. As we've already heard, eclipse timings are essential in determining periods of stars, but the most important thing they give us are changes in periods. So, unfortunately, when we look at stars, we don't see this. This is not even an artist's impression. This is comes from a model. So you have, as was described earlier, the Roche lobe of the larger star. This is a contact system. So you have the Roche lobe of the larger star and the smaller component, and most cooler eclipsing binaries are plagued by spots, and they're usually cool spots. Although some warmer regions must exist on these stars, but they are generally deemed to be cool spots, and that's what seems to work best. So let's. There are. I'm only going to talk about the three main types of eclipsing binaries. So we have the algol types, which have well-separated eclipses, the beta Lyrae type, where the light curve is continuously varying, and the W Ursa Majoris type, where the eclipses are very similar, and the light curve is also continuously varying. These systems are essentially in contact. These they may be semi-detached, or in the case of algol binaries, they may be completely detached. Beta Lyrae stars can be semi-detached or detached. Now, the light curves of eclipsing binaries provide an enormous amount of information that you just don't get from single stars. The mutual interaction between the two stars as they go around each other provides information on both the components in different orientations, and so you're able to build up an incredibly useful picture of the diameters, the masses of the stars, and indeed their distances. Photometric distances are now becoming very accurate, and one of the main benefits of these main results from these eclipsing binaries. The other important thing, which is more relevant to us, is that eclipse timings provide data on period changes in the systems where there is some sort of interaction going on, and that includes all of these types when they are semi-detached, when at least one component is filling its Roche lobe. So we're going to do a bit of stellar evolution. The evolution of binary stars is driven by the evolution of single stars. So we start off with, on the main sequence, with hydrogen fusion in the core, and over, in the case of the sun, some 10 billion years, the sun will evolve slowly through its hydrogen burning phase. At some point, hydrogen burning in the core will become exhausted, and it will start to move off and become a red giant. You get hydrogen shell burning, and then there is this dramatic change in luminosity and cooling, and you end up at this point at the tip of the giant branch, and that is where a helium flash occurs, and helium starts burning in the core. Now, for low mass stars, this is a more intermediate mass stars, but for low mass stars, they never get to burn anything else, and they will go off down this way. For stars that are sufficiently massive, they will return up the asymptotic giant branch, and there they will have a cure of helium, and then they will start burning carbon and oxygen in the core, and you will start to develop this shell that you all must have heard of, where the different elements are being burnt in shells around the core. Now, up this point, everything, whatever happens, whatever goes on depends on mass. So there are all sorts of variants. If you have two stars, there are all sorts of variants that can happen. So we'll just leave it there. If we look at this in a bit more detail, so here we have the zero-age main sequence for different masses from about 1 up to 25 solar masses. The important point here is that the radius increases in this direction. There are convenient lines on there. For low mass stars, there is the transition from helium, hydrogen core burning to shell burning is relatively smooth. But for stars more massive than about 1.1 or 2 or 3, depending on composition, there is this jump, this little feature here, and that is due to the core in stars that have convective cores collapsing a little bit, so it has a little collapse because hydrogen has been removed throughout the whole of the core due to convection, and it has to have this little compression to reignite the hydrogen in a shell. But then they will move off over towards the red giant branch, and then these are tracks, asymptotic giant branch tracks for more massive stars. Now, the important point is that and this distinction here between the stars with radiative cores, the lower mass, and convective cores makes an enormous difference to what happens later on in the star's evolution. So we have here in millions of years, slow evolution through the main sequence. We then have the journey up to the giant branch, and then later evolution for more massive, well, for stars 1.6 mass. During this phase, if the star fills its Roche lobe, during this stage, that leads to what's called case A mass transfer. If it transfers mass during this stage, it's called case B, and this case C only happens for very wide systems. So these systems, when it's all on the main sequence, the stars are short period. These will be more intermediate period, and then for these are very long period stars. Okay, so mass transfer, whatever stage it is, however large the system is, the primary evolves and exceeds its Roche lobe, and matter is transferred to the secondary through the L1 point, and this is a messy process. It is transferred through an accretion stream. It may fall directly onto the star, or it may form it will almost invariably form some sort of disk. As the mass ratio starts off at less than 1, it will tend towards 1. The period shortens, and the Roche lobe around the primary star, the one that's donating the mass, shrinks, and also the in relative terms, but also the radius of the system is decreasing because the period is shortening, and so that has positive feedback, and it drives this incredibly high rate of mass transfer during the early stages. When the mass ratio reaches equilibrium, so both stars have the same mass, you get a period minimum. The mass starts to transfer. The mass transfer continues, and then the mass ratio slowly reverses. When you get to that stage, the period increases. The size of the system begins to increase again, and with it, the physical size of the Roche lobe increases, but the relative size of the Roche lobe decreases because the original primary is still losing mass. And then at some point, the original primary detaches from its Roche lobe and mass transfer eventually stops. And typically, the mass ratio is more than reversed during this process. So you end up with a very different looking system. Now, there are all sorts of uncertainties in this. One of the large uncertainties is how much mass is lost from the system. And that will obviously affect the way the system evolves. But the lost mass also carries away angular momentum. And this can be very important. One of the other uncertainties, of course, is the uncertainties in single star evolution models. You're relying on those to tell you when the mass is going to be transferred, what sort of size, and all the other parameters of the system. And that there are all sorts of things that depends on. Rotation and mixing of stuff in convective systems it's tricky to work out. And of course, there are magnetic fields, and as we know, they complicate everything. So, yes, this is grossly grotesque simplification. Case A, we'll start at the bottom here. Case A, W Ursa Majoris stars are main sequence stars, and so they are always formed by case A mass transfer. W Ursa Majoris stars form well before the terminal age main sequence, so they are well solidly into their main sequence evolution. Algol stars are mostly produced by case A mass transfer. beta Lyrae type stars, late case, they are somewhere near the boundary of case A and case B. So those stars are leaving the main sequence. Beta Lyrae stars tend to be case B. Beta Lyrae itself is a case B type mass transfer, but ultimately Beta Lyrae stars at some will look something like algol systems, but long period systems. And then we get onto the larger systems, where you end up with systems having a common envelope, and these produce white dwarfs and will ultimately go on to produce an enormous variety of systems, including various CVs, supernovae, and the same is true of these very large systems. CVs are generally thought to be produced by relatively wide, low mass systems, which undergo very late mass transfer. They end up going through a variety of possible common envelope phases, and you end up with white dwarfs of different compositions, either helium stars or stars with carbon and oxygen in the core. So, what sort of period changes can we see? Stellar evolution. Obviously, we can't see the long time scale, but we can see rapid phases of stellar evolution. One of the other things that we can pick up from eclipse timings are third bodies, and these are light travel time effects, where the main binary is reacting to another body that's going around it, and that will have an impact on the timing of the eclipses, and so that can be used to identify other bodies in the system, and that is important for statistics of binary stars and stars with multiple systems, and in some systems, extra bodies may be a mechanism for removing angular momentum from the system. Apsidal motion is where you have an eccentric central binary, and the action of a remote third body causes the central binary to precess, and that can be used to determine information about the internal structure of stars, and that's really one of the only ways of doing it. The other thing about apsidal motion is that if the binary is at a relatively high inclination, then as it precesses, the eclipses can change. They can become fainter, and they can indeed disappear as well. Not as obvious is that it's possible to see magnetic effects. Angular momentum loss through magnetic braking is one of the main mechanisms for reducing the periods of WS Majoris stars and cataclysmic variables. So that is an important thing. That is a secular process that should go one way. And then there's another mechanism called the Applegate mechanism, where the angular momentum of a cool star is affected by its magnetic cycles, and that can end up in the the dynamics of the system and actually moderate the period of the system, and that should be quasi-periodic. As the magnetic field of the cool star changes and goes through its cycle. Now, there's this is nothing to do with any of those, but this is eclipse variations in this star, which is a WS Majoris system. And here we have, this is test data, and you can see this is the primary eclipse, and you can see the purpley points there are from different times, different runs, and the greeny points there. So those all are consistent. In this one, the blue and purple points are on the inside, and then they slosh around to the other side. And that indicates that the period is changing. Now, in fact, the period is not changing. It's just that there are huge spots sloshing around on the surface of the star. But the astonishing thing about this is that it happens very quickly. One of the problems with eclipsing binary timings is that the scatter in the measurements is always a lot more than you'd expect, given the accuracy with which the times are measured. And this is clearly one of the reasons why. So these are eclipse timings of 477 eclipses of this binary over each one of these panels is about 12 days. These two are continuous. These two are separated. And you can see that the position of the secondary eclipse relative to the primary eclipse has moved by a few thousandths of a day on a relatively short time scale. And it's done the same thing again here. There's less movement here, but it is different. And there's less movement here, but again, it's different. So this is one of the problems with measuring eclipse timings. The star, if you remember the original picture with the spots, those spots clearly move on a short time scale. It was known that they moved over some time, but this clearly shows that they move on a very short time scale. Right, this is Beta Lyra. This is Chara data. So this is the high resolution interferometry data from the instrument you saw earlier that Jeremy showed. So this does look a bit like Saturn on a bad night, but it's those are some milliarc seconds across. So this is incredible. This is at the limit of what is possible, which I think is quite astonishing. But the period of that is best part of 13 days. So if we look at Beta Lyra, this is the O-C diagram of Beta Lyra from the first observations of Goodricke up to some of the most recent observations. The yellow ones are visual, obviously. The blue ones are photographic, and the rest are photoelectric or CCDs more recently. Beta Lyra is not an easy object. It's always talked about as a beginner's star, but it really isn't. It's difficult to observe, and it's difficult to observe accurately. But you can see the period. The period's 12.9 days, but you can see that the timing has changed by 40 days this way and 40 days back again over the time that it's been known. So this is an absolutely prodigious change. So the O-C residuals here are simply the difference from what you would expect if the star had a constant period. Now the line is a parabolic fit to the data, and that is what you would expect if the star is constantly changing at a completely regular rate, and all the evidence suggests that the period is changing in a completely continuous, smooth, and regular way. These are the residuals from the residuals at the bottom here. So this is the residuals from the fit, and it has a period of 12.9 days, and the bulk of the residuals are within half a day. So that's given how difficult it is to observe, it's quite an achievement, really. Right, this looks a bit of a mess. So this is the evolutionary model for Beta Lyrae. It's not immediately obvious, but the primary starts off there, and the secondary starts off here. So the primary evolves through the main sequence. It just hits the case B type mass transfer, and then it dramatically whips down here to cooler temperatures as matter is removed from the primary, and then it slowly recovers. And I'm not sure what these details are, and then it goes through some further evolution. Currently, Beta Lyrae is reckoned to be at this point here for the primary. The secondary gains mass and makes a more or less smooth and continuous movement up to this point here. So that has gained mass. It's become hotter and brighter. The size of these symbols indicate the size of the star. Now, there are various attempts at modelling this. This is just 3 of them. So the initial masses were reckoned to be, or taken to be, 9.9, 7.7, 10.4 and 7, 12 and 7.2, and with these periods 4 and about 2.5 days. The age is reckoned to be, is calculated to be 23 million years. The system is currently 147,000 years after the Roche-Lobe contact. The rapid mass transfer phase finished 34,000 years ago, and it will become detached in a further 72,000 years. So on an astronomical and stellar evolutionary timescale, those are pretty short. I mean, it's not like a supernova, which is very short, but it is still quite short. And interestingly, it will end up with a period of 23.5 days by this reckoning, and masses of 1.8 and 13 solar masses, or best part 14 solar masses. So, of course, in some time, perhaps not too long, the primary itself will start evolving away, and you will end up with a very complex system. Right. Okay. Okay. So this is the photometric model of Beta Lyrae. The radius of the primary is about 6 solar radii. It has a optically thick disk. The central star itself is not visible. All this is material that's heated by the star. It is a very complex system. It has a spot between the disk and the original primary, This is now the more massive component. There's evidence of jets, a bipolar jet, and there's also evidence of another spot somewhere around the disk. So it's a complex system. Right. Now, how do I make this move? There we go. No, it's done it. So this is a canonical view of an algol system, and these. So the original primary is is now a cooler, lower mass star. It's still sending material through the inner Lagrangian point to the mass gaining star, which is which has a disk around it, and this is probably the origin of BE stars as well. And there are some BE stars are thought to be essentially algol systems. And there's a disk. There are spots on the surface of the secondary, of the new secondary, and there are jets and an enormous number of hot active regions around the primary. Now, algols are supposed to be in the stage where most of the mass transfer has occurred, and so they are in a slow stage of mass transfer from the secondary, the new secondary, to the new primary. So the period should be generally increasing. Now here we have an O-C diagram for Z draw, and the general shape of the O-C diagram suggests that the period is more increasing than not. But there is an enormous amount of detail and activity in this, and there are these very sharp changes in period. There are these little details. Although these are visual observations, they are clearly consistent, and there is this long, almost continuous, almost constant period here. So it is very difficult to interpret that, and it certainly doesn't look like something where the period is changing slowly. Here we now have another algol type. This one has an enormous change in period, and generally it looks as though the period is on an increasing trend, but there's certainly nothing continuous about it. It is largely constant here, and there may be there's obviously other activity in there as well. Here again, this time the period seems to be decreasing, but there are sharp features. That looks like it's continuously increasing. There the period is constant. The period looks really constant there as well. So there's nothing, that is not a simple change. And here again we have something where the period is decreasing, and it is a complex picture. So this is, I mentioned earlier about apsidal motion. This is what apsidal motion looks like. The eclipses, the primary and secondary eclipses, mirror one another instead of moving together. And they tend to be on this sort of scale, a couple of hundredths of a day. Right, okay, yeah, right, we're not going to have, let's just, okay. So the evolution of WS Majoris stars is driven by magnetic braking. And let's just see what we get. Okay, so this here represents the dichotomy between the cooler stars and the warmer stars. So these are the ones that presume the systems where at least one of the components had a convective core, and these cooler stars are the ones where it has a radiative core, and it leads to significant differences in the evolutions of the system. So WS Majoris archetypal system. It has a very complex behavior. It is not clear what is going on there, but it's clearly on a short time scale. Here we have another WS Majoris system, and here there is an indication that the period change, although it is generally decreasing, is made up of linear segments. And there's also evidence of a third body in this system as well. And here we have one where the system is on a generally increasing period trend, but this curve is not symmetrical, and again it seems to be made up of straight line segments, again with the possibility of third bodies. Yes, right. I'm wrapping it up now. So in this one, VZLib, there are clearly constant period sections which work in opposite directions. Here the period's increasing, and there it's decreasing. And in this, and at the end here, we have two components, two bodies. That's a short period third body, and then a longer period third body. Right, cataclysmic binaries. Evolution, as I mentioned earlier, goes through the common envelope phase, and you end up with a white dwarf of half to one solar mass and a cool star. And for the stars that end up as dwarf novae, they appear with a period of about 1 day, and then angular momentum loss is supposed to decrease the period down to about 3 hours, where you meet the period gaps. And David will go through this in a lot more detail later. Here we have two systems where the period is clearly increasing, which it shouldn't. And here we have a couple of stars where the activity is unusual. So period changes, can we see them? Yes, 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 yes. Can we? The main thing is that we see things that we don't understand. There is a lot that we don't understand, and it's most probably magnetic effects of some sort. So is it worthwhile doing it? Yes, of course it is. Otherwise I wouldn't be here. Most eclipse timings are made by amateurs. The whole area of science relies on amateurs making timings. Now, professionals do it as well, but they don't do it in the numbers that professionals do. Surveys are useful, and you can learn a lot about eclipsing binaries from surveys, and indeed you can get eclipse timings. But who knows how long they are going to be about? They are migrating towards fainter magnitudes, larger telescopes. So how long is Assassin going to be there? It's useful at the moment, but yeah, we need to do it. That means you lot need to do it. Right.
We're going to have to stop there.
Yeah.